Thanks a lot, Brian, for the introduction. No picture of me, huh? Welcome to the talk on moveit. I'm Sachin Chitta. I work for Willow Garage. I've been there more than 5 years now. The other people on the team, Ioan, who Brian already introduced, Acorn Pulley, who's sitting next to Ioan, is also a key member of the moveit team. And of course, we can't do this without a community of developers. So there's a huge list of people that we want to thank, and it's just impossible to list everyone on one slide. But I would like to recognize all the people at Willow, all the names listed there for helping out, and the ROS and PR2 communities for being so helpful. Over the last 5 years, we've seen a great deal of interest in the personal robotics area. So it started quite a while back. The PR2 came out I think we released it actually about 3 years ago at ICRA. In the middle is the Carobot, which was developed here at Fraunhofer IPA. On the right is the Herb robot from CMU. And the research in personal robotics was driven by this idea of being able to have robots in the home. And the cool part of what happened over the last 5 years is we kept pushing the cutting edge. So personal robotics in the home is hard. You have to work in human environments where you're going to be right next to the people, and safety is incredibly important. But the advantage of pushing on something like this on the research front is that a lot of technology was developed. And although all this technology is not mature, we can now start thinking of applications where some of the technology we've developed can actually enable something new, something novel, something we haven't seen before. And we've already started to see that a little bit, and it's starting to happen more on the industrial side, more on the services side. So on the left is a big KUKA robot. It's an omnidirectional base with a big KUKA arm on it, used for inspection tasks. So this is a mobile manipulation robot actually out there, and it's probably going to get deployed in the next few years. And on the right is the robot work, which you can go out and see in the IPA booth. And again, this is you can see a path to actual applications coming along with these kinds of robots, especially on the industrial side. So it's a fantastic time to be in this area, and it's for us, being the developers of a lot of the software, it's a fantastic opportunity to see all these possible applications that can come out. So what is moveit? Moveit is new software. We've been building it for the almost the last couple of years. And basically, it's a software that integrates motion planning, kinematics, control, collision checking, with an eye towards applications which in mobile manipulation. So this does not mean just mobile, but also fixed manipulation tasks. So it includes integrating perception, grasping, control, navigation, and manipulation, so that you can do new, interesting applications in a lot of areas. And so over here, you see two robots working in the Arvis visualizer with moveit. On the left is the Motorman robot, and on the right is the PR2. And we're going to show you a little bit of a live demo towards the end of this talk for this. And what really motivated us, why are we doing this? We want to build a state-of-the-art platform. We want to take everything that is on the cutting edge, everything that we've developed and other people in the community have developed over the last 5 years, targeted maybe towards personal robotics, service robotics, and offer that as a common platform. Just like ROS allows you to build all these capabilities, moveit lets you build capabilities which integrate specifically perception, manipulation, and navigation. And really, when we started off, we said the simple motto for us is simple things should be easy. If you want to do something simple with your robot, you have a new robot and you want to get up and running, it shouldn't take days or weeks for you to integrate that robot and start get up and running. And so it was really important for us to provide an out-of-the-box experience. So we wanted to make sure you get the software and you can get running literally, at least with the visualized version of the robot, within 15, 20 minutes. That's what we were aiming for. And I think we've actually achieved that. So we have what's called a tool called the Setup Assistant, which I'll show a little bit, a couple of videos on that. But basically, the idea there is to start from the ROS representation. So start from the URDF and be able to play with the robot within a very short time. The other thing that we looked at is easy-to-use APIs. We wanted to make sure there was an API defined at multiple levels. So if you are an advanced developer, you know what to do with moveit, but at the same time, we really wanted to make sure that people who want to live higher up the stack, so they just want the capabilities, they don't need to dive deeper, can just go in easily and start working with moveit. So along with simple things being easy, we wanted to make sure that if you really want to get in and do something new, because this is still a new area, we don't have all the solutions, and if you wanted to do that, you can dive deeper and address all the harder problems. So moveit is designed to be flexible, and the way we architect that is by making most of the components plugins. So that way, if you want, you can plug in your custom component and use it for anything you want. And really, the key for us in terms of design decisions was performance. We want moveit to get to a stage where if you're a company or you have a product and you're putting it out and you say, okay, I want to ship software with this, we want you to look at moveit and say, if I want my robots to be moving, moveit should be doing that. That is our motivation for a lot of the design decisions we've made. And that's why we've been making attempts to make this as high performance as we can. So on the technical side, if you look at the way robots are integrated now, new robots, it takes way too much time to start up and do things. And what we're giving you is a set of capabilities so you can move higher up the stack. We want to try and take care of some of the lower level things so you can move higher up the stack and spend most of your time developing applications rather than working on the basic stuff. And one of the keys, key technical areas that we wanted to address is environmental awareness. So these are robots now, these are applications where the robots will be moving around in possibly cluttered workspaces. There'll be people in the workspace, and so it's incredibly important to have good situational awareness. And there are multiple ways of doing this. What we wanted to look at is integrated 3D perception. So being fully aware, or as aware as you can be, of the things around you so that you stay safe. The other key thing that we think is important is motion planning. So because these are dynamic environments, things are constantly changing, you want to be able to react faster. And we're also focusing on constraint manipulation tasks. So if you look at a lot of tasks that robots have to do in the real world, there's a bunch of constraints that you have to deal with. And I'll show you some examples of that. So moveit has evolved from the ARM navigation pipeline and the grasping pipeline. So if you're familiar with a lot of the manipulation stacks in ROS, you'll recognize that this is work we had done a while back. But we did look at what we had done. We looked at feedback from the community in particular. We want to thank you all for telling us what you liked about these stacks and what you didn't. And we took all that and incorporated those lessons learned into moveit. So it is essentially a rewrite almost from scratch. We've made an attempt to keep the ROS API almost the same, but as I'll explain, we've done things differently, but for a reason. So I wanted to show this video, which is sort of summarizes what the state of the art was with the grasping pipeline and ARM navigation. So this shows the entire pipeline, all the way from starting from taking perception data. So this is 3D sensor data from a Kinect, filtering it, building an environment model. So in this case, we're basically building an occupancy grid-like model using the Octomap package, but we augment that. So we add, because you don't want to be dealing just with object voxels, you want to actually deal with object representations, so you can input things from, say, object detection techniques, be able to identify objects, put them into the environment, and then do manipulation with them. So there's two types of grass planners that we have, one that can directly deal with point clouds, and the other that deals with grass that have been computed offline. So really the focus was, with all that we've been doing, is trying to get to a stage where we can offer almost a package set of capabilities that you can deploy very, very quickly. That was the focus. And you can see this happening with the PR2 robot here, but the cool thing is, once we started putting this out and the code out and the videos out, more people started looking at these techniques and saying, okay, how can we use these in other applications? And there's a lot of robots now using our software. And you can see that the variety sort of is incredible. We go all the way from the K-robot on the top left. That is a mobile manipulation platform developed here at IPA. There's the UR5 and the Modeman robot to the right of it. In the bottom left is a EU project. That's a fixed manipulator, not a mobile manipulator. Then there's the Rob at work. Our stacks have actually been run on the Robonaut. If you come to ICRA last year, that was the demo you were seeing. On the DARPA robots, the TOOM robots with the KUKA lightweight arms, and also the NOW. So it's an incredible range. This is not just, so ARM navigation had the word ARM in it, and people assume, okay, this is just for ARMs, but we're no longer restricting ourselves to ARMs. So you can probably imagine using this on a quadcopter. It hasn't been done yet, and we would love to see the first person to do that. But the cool part is, once we started putting this out, people started noticing this, and this is actually a series of demonstrations done by the Ross Industrial Consortium. This is the consortium led by Southwest Research Institute, and Sean Edwards, who's here somewhere in the audience, came over to Willow Garage and worked with us on taking exactly the same software you saw running on the PR2, modifying it, and the modifications were not major, mostly on the configuration side, and starting to use it with a completely different robot. It's a completely different arm with a completely different gripper. So this is a Robot IQ gripper, and you can see there's a Kinect. If you look in the video, there's actually a Kinect mounted behind the robot. So this is incredible. This is what we would like to see happening, that you get a robot, you unpackage it, and you say, okay, it either comes with moveit, or you're going to install moveit on it, and you get going immediately. This is what we would like to achieve and give you these capabilities so you can start thinking of more higher level applications that you can work on. And the first set of robots we tried moveit on were not the PR2. This is actually video from the first simple demos that we did right when we started using moveit. And so you can see on the top left is actually the UR5 arm, which we had at that point, and the bottom is the Modeman arm. So it's not just the PR2. In fact, moveit is robot agnostic. You can set it up with almost any robot and be able to get up and running quickly. And I'll show you an example in a second. And so it's incredible how quickly these things are progressing. This is a demo from the ICRA booth, the EPA booth at ICRA this year. So this is just video. This is fresh video from last week. This is moveit running on RobotWork. Ioan spent some time here with the EPA folks and helped them integrate it. And some actions are being run on moveit, not all of them. But you can see that immediately you can see all these applications coming into mind where you can start doing mobile manipulation actually in industry, in service robotics situations, and that's very cool. So let me switch and talk a little bit more about what moveit gives you. This is a list of capabilities, not necessarily complete. There's a lot of other things that moveit can do for you. But the core set of capabilities includes collision checking. So we've made a large effort to try and get state-of-the-art collision checking into moveit. Integrated kinematics. The idea with this is you start using this and the robot just starts working. You don't have to think about writing your own IK solver initially. You don't have to worry about integrating it. It just works. Motion planning, and I think we have probably the state-of-the-art, as in the best set of motion planners that you can possibly get anywhere. And really integrated perception. So moveit actually integrates perception on the 3D side and does a lot of that for you. We've been working pretty hard and in collaboration with a bunch of people to try and standardize the interface that moveit operates, because that's the one thing that we want to make sure happens right, because controllers usually are provided by the vendor, and we wanted to make sure there's some standardized interface available. And moveit also does execution and monitoring, and I'll show you some videos of that. And the other set of cool applications I'll show you is kinematics analysis. So this is useful if you're designing a new robot and want to figure out how it will do in different situations. So this is a very high-level diagram showing what moveit, sort of a system-level architecture of moveit. And really, you as the user are going to live up there at the user level, and you have multiple ways of getting into the system. So we offer a visualizer. So this is a plugin to Arvis, the regular ROS visualizer. What this lets you do is get up and running incredibly quickly. It also lets you interact live with the robot. So you can move around the end effectors, you can set plans, you can execute plans from there, you can import CAD models if you want, you can visualize all your sensor data. So this is an incredible way to get started with your robot. We also offer the regular set of ROS interfaces, so these are actions that you can incorporate into your programmatic applications. But we also made an effort to provide a scripting interface, so making simple things simple. So if you want to move the robot to a point, that should not involve 100 lines of code. That should be done within 3 or 4 lines, less than that. And I'll show you an example of that as well. So really the focus here is on providing a good user experience, and that's very important for us. So getting down into the actual components, for collision checking, we offer 2 libraries. So one is FCL, which is the flexible collision library. And really what we've done is taken a lot of the state-of-the-art here. So we work with Dinesh Manucha, who develops the state-of-the-art in collision checking. And we've taken a lot of his libraries and pulled them together into one package that you can use. So FCL it gives you about 3,000 full-body collision checks per second for the PR2. The cool part is it does that with real-time sensor data now. So the data coming from the Kinect or from any 3D sensor goes directly into the Octree representation, which is Octomap, and it's a native data structure inside FCL. So you don't even have to convert anything, you just pass it in directly, and FCL knows how to deal with it, which is an incredible advantage. And of course, FCL is doing mesh-to-mesh collision checking, so that gives you a pretty high fidelity collision checking. The next thing is proximity collision detection. So that is slightly different. It uses an approximated model. So on the left, you can see the approximation of the model for the Pier 2 using a bunch of spheres. It uses a 3D distance transform, so that way you can figure out actually the distance to the nearest obstacle. It's very fast. So you can see there's almost an order of magnitude difference. The drawback is it's not as accurate. But there are a lot of applications where something like this is enough for you. And the fact that it's so fast offers a lot of advantage in some applications. On the motion planning side, like I mentioned, we wanted to keep everything flexible. So all the motion planners are integrated through a plugin interface. So this allows you to start using, if you have your own library, all you have to do is wrap it in a simple, using a simple class, and you can go start running with this. And through moveit, we can integrate any set of motion planners with your robot. The ones that are automatically configured right now, the main one is OMPL. This is the Open Motion Planning Library. Gives you a bunch of sampling-based planners, and it is a really incredible code. The software won the Open Source Challenge Award last year, and so it's very well tested. It's our workhorse, and this is the one that we recommend for a lot of applications. For more search-based stuff, so if you're doing navigation and you want to use more A-star type of planners, we have the search-based planning library. This comes out of CMU. OMPL comes out of Rice University. And we offer an integration to both of these. So let me talk, I mentioned how easy it is to get up and running with moveit. And this is actually a live demo. This is, sorry, it's not a live demo. It's real time, as in it's not sped up video, but it basically shows you how you can import a robot model into moveit, into the setup assistant, and basically start working with moveit. A lot of the steps you're actually seeing being done here are optional. You don't have to do a lot of these. Mostly, you just have to define what's called the SRDF, and I think Ioan will show you a little bit of a demo of that. But you can see how quickly you can get up and running with the robot model. So you can start, there's a bunch of things that you have to do. So you define how the robot is connected to the world, because this is not something that's available through the URDF right now. You can add robot poses. So in different cases, if you have home positions or particular positions that are frequently important, this is how you would do it. You basically save the generated configuration package, and you're up and running. That's it. And if you have the URDF, it should not take you more than 15, 20 minutes in most cases to get from the point where you load up the URDF to the point where you can start doing this, which is, we want to make sure this works as quickly as possible so you can start playing with your robot instantly. And we think we've been able to get that running. So you can see you can compute motion plans. You can also do all kinds of other stuff that I'll show. And as I said, moveit is not only for the arms. You can plan for the base as well. So in this case, you can see Ioan moving the robot around so that there's some distance between the base. This is a simple example, but what we wanted to emphasize here is that unlike arm navigation, moveit is general. So it's robot agnostic. It's more general, where you can do much more complicated things than just being able to do stuff for an arm. And as I mentioned, moveit integrates perception. So it actually does this for you. So if you have any source of 3D data, so it could be a typical 3D sensor like the Kinect, it could be stereo cameras, you can directly plug that in to moveit so that it knows what the environment looks like. So this is an example. This is actually an integration with Gazebo. So this is an example running in Gazebo where you see the robot first performing a motion motion in free space, and you can see the corresponding motion in simulation. And then we're going to put in a box in here so that the robot can actually do perception based on that. And the key here is that it's incredibly easy to set this up with any sensor that you have. And this was one of the most important things we wanted integrated into moveit. So in this case, you can see the robot knows about the part of the box that it sees. You can still interact with the robot and move it around. And you can see that when it thinks it's in collision, it'll tell you by changing the link. In this case, we're actually setting up the goal, motion planning, and you can see it avoids it. And you'll see the corresponding motion in simulation as well. And what this really enables, and what we were aiming for, is applications like this. In this case, Acorn. This is from the ICRA booth again last week. And you can see a live demo of this at our booth. We brought the PR2 over. And what Acorn is doing is walking around and then interfering with the action of the robot. And what the robot is capable of doing using moveit. So the first thing it does when it detects an impending collision is it'll stop. And the default behavior right now is to wait for about 2 seconds. So that gives you time to step away, because in most cases, a lot of these things happen because people are in the workspace. So it gives you time to step away. And if it doesn't, then it'll actually plan around you. And it does that pretty fast. The delay you see is more a programmatic delay and not really with the planning itself. And the other key technology that you don't really see here, but it's in there, is that it's doing really fast self-filtering. So it's filtering out the links of the robot incredibly fast. And what this really enables is applications where people need to be working closely with the robot. So this is based more on a visual sense of the world. We have other examples right here with the Baxter robot, which takes a slightly different approach to doing these things. But you can imagine a lot of new applications coming out based on that. And as I mentioned, you can directly import CAD models. So this is actually a CAD model imported to the world. You can do that if you'd like, and actually mix and match with sensor data. So you don't have to work just with this. Everything in moveit is represented as a constraint. So when you think about going to a particular place, you're not saying just go to a particular joint position. That's actually a constraint saying, go to a goal position where the joints are within these limits, and those limits are really small. But there's a set of native constraints that comes with moveit. So there's joint constraints, position constraints for if you want to do end effector constraints, orientation constraints, and visibility constraints. In addition, because of the plug-and-play capability, you can define your own set of constraints as well. So this really makes it flexible, and this is one example of the robot operating with orientation constraints. So typical applications in human environments, you might want to keep things upright as you're doing something. We made a huge effort to make sure that all the things that we're doing are sort of right and up to the state of the art. And to do this, what we did is develop a benchmarking suite. So essentially, what we're looking to do is benchmark all the components that we're working with. So in this case, this is the motion planners, so that not only can you see and sort of believe the numbers, but also you can choose. So you can figure out which set of techniques is useful in different situations. So these are some examples of the kind of information that we can get out of moveit, and really the focus there is on maintaining quality. So making sure that everything is regression tested and that things don't get worse as we keep developing. So another cool application that I wanted to mention is kinematic workspace analysis. So as we were doing different projects, we realized there's a need to be able to evaluate robots that we might be building. And we couldn't find any tool for this, so we went and built our own based on moveit. And really the two applications we were looking at is robot design evaluation. So you have a new robot, you have a set of tasks that you want to execute with the robot, and you don't really know before you design it how well it'll do. And what we wanted to give people is a tool so they can test that. So if, for example, when we designed the Pier 2, we looked at, can this robot reach shelves? Can it reach high shelves? Can it reach drawers? Can it reach the floor? What does it need to do that? Does it need to raise the torso? And we really didn't have these tools then, so it was hard to figure out some of these things easily. We also wanted to see, can it open doors, for example? And we couldn't really do it without actually either doing a full simulation or being able to do it on the robot. And now, with moveit, you have what's called the benchmark tool. This is a tool that lets you play with different robot designs. So you can basically input a URDF. You can create a set of problems. So you can basically say, I want this robot to be able to reach all these positions in its workspace. It'll automatically do that computation for you. It'll come back and give you statistics. How many can it reach? Which positions can it reach? What are the joint angles? You could even imagine putting in different metrics. I'll show you a couple of them a little bit later. So you can have a lot of information that you can use in your robot design. And basically, this is a tool that will let you, if you're designing a new robot, it'll tell you how good is your robot going to do in different situations. And the cool thing is you can also do Cartesian trajectories. So if you're thinking of doing tasks like door opening, you can set that up sort of almost natively. You can test that and have moveit show you how the robot would actually execute that. And it's an incredible tool when you're doing new kinds of robots, because you'll be able to look at this and say, okay, I need to change my design so some of these things are much more possible. And this is actually a comparison of the Pier 2, the KUKA lightweight arm, and the UR5 in a set of reachability tasks. So in this case, we're trying to get it to reach a bunch of shelves and a bunch of locations on shelves. And you can see that the industrial robots do pretty well in terms of workspace, much better than the Pier 2. The other application, if you have a fixed robot, like an industrial robot, and you want to figure out where it should be in the workspace, this set of tools will let you decide. If you have a bunch of positions, it'll let you decide where you can put that. And also, if you have a mobile robot and you want to go and grasp things. So typically, one of the biggest issues is if you want to grab something, where do you put the base? And moveit helps with that. There's a few other things that moveit can do. So for example, you can associate metrics with different robot configurations. So in this case, we're looking at 2, which is manipulability, which is a measure of how well the robot can move in different directions at a configuration, and payload. So how much can the robot lift in different configurations? And so you can see in the RViz visualizer, you can enable a bunch of metrics, and moveit will show you those computed things right on the screen, so you can use that. So it's an incredible set of capabilities that I would encourage you to look if you're starting to design new robots. But the other key set of capabilities that we want to offer almost packaged is pick and place. And this has been one of the big focus areas at Willow for quite a while. And we want to take all the knowledge we've generated over the last 4 years in this domain and basically package that together so you can start using this quickly. So we're not all the way there yet with moveit on this, but we're pretty close to where we can have really fast package application. And the real key is that we did things differently. This is a picture of the old grasping pipeline. And the way it did everything was sort of a serialized operation. So it basically had a bunch of things that it wanted to do. And it would do each of these in serial. So if you wanted to grab, say, this glass, it would first figure out, okay, there's maybe 40 grasps for that glass. For each of those, it would compute a bunch of motions and say, okay, is this possible or not possible? The issue was that you would basically, if the last grasp was the right one, you would have to step through all of them before you realized, and it was inefficient. It was slow. You had to work through the whole pipeline to get there. And one of the big things that we've done in moveit is restructured this entire pipeline. what we said is that instead of doing all these things in serial, we're going to do things in parallel. So we have this concept of a manipulation stage. Basically, this is a series of operations happening in parallel. So you bring all these up. So you bring up grass planning, you bring up inverse kinematics, you bring up the motion planners, and each stage fills the next one. So as soon as it gets a grasp, it'll pass that on to the next stage. As soon as it gets a motion plan, it'll pass that on. And these stages can go up and down in priority, depending on where they are and how well they're doing. And this way, the key to doing manipulation in unstructured environments is to make sure that you have a lot of alternatives. And what we're doing here is exploring all those alternatives as quickly as we can so that we get to a solution much faster. And so this is one of the first examples of moveit running pick and place. This was just last week. We don't have everything working yet, so I won't claim that you can just go and run this out of the box. But in terms of the actual pipeline, the actual components, I think we have a lot of it in place, and we should be able to get things running pretty quickly. As I mentioned, we focused on a simple API. This is what you need to start moving in ARM. That's it. This is in C++ code. It's basically really simple API so that you can get up and running incredibly quickly. Whether you're a beginner or whether you're an advanced developer, this is how easy we want it to be. I should mention what the differences are between moveit and the old way of doing things. So in ARM navigation, we had a bunch of different processes, each one of which was doing a particular thing. So inverse kinematics would be running in one, it would be maintaining its own version of the world, motion planning would be running in other. And we quickly realized that because we're dealing with integrating perception so much, we don't want to be passing all this data back and forth between nodes as much as we do. So we changed the way we do things. So moveit, most of the capabilities you get in moveit happen in a single process. They don't happen in multiple processes. There's one instance of the environment being maintained. So this gets rid of a lot of overhead in terms of transport. And the other thing we did is we separated the computation from the communication and configuration. So that still happens to ROS, but the core set of capabilities, for example, motion planning, collision checking, these happen inside C++ libraries. And the idea is that if you're developing applications and you want just that part, you can get that if you want. And like I said, we emphasize speed and efficiency, so we've spent a lot of time parallelizing or making the collision checking capable of being parallelized, kinematics also, and all the other components as much as we can. And this is just a summary of some of the differences for different components. I won't go into too much detail here, but the highlights are basically we focus on performance. We're trying to integrate perception so that you have out-of-the-box full, as much situational awareness as you can. We had a huge focus on reactive motion planning, so this is being able to react in collaborative environments. And the really important part, we're trying to make it easy and user-friendly at different levels. So if you're a beginner, if you're an advanced developer, we want moveit to be as easy as possible. And for you to be able to use it really easily, we want to offer you almost out-of-the-box experience with a lot of applications. This is the key for us. So there's a full wiki with a lot of documentation at moveit.rust.org. There's all the code is on GitHub, and there's of course the regular issue tracking. So if you have any issues, you can put them in. For the community, there's a community mailing list at moveitusers@googlegroups.com. We encourage you to, if you have any questions, any concerns, to email us so we can help you develop your applications. And where we're really going with this is we're looking into what does it take to use moveit in products. That's, for us, the key. I know there's a big effort on the ROS side to do the same thing, is to start thinking about what does it take to get ROS into products. Maybe it's already out there and we just don't know. And of course, we're interested in developing enterprise-level capabilities for manipulation, for perception, basically integrated manipulation, perception, and navigation. So if you're interested, please let us know. For general questions, that's our email address, moveit@willowgarage.com. And with that, I'll stop and let Ioan set up while I take questions.